Hi, I'm Anay Mehrotra. I'll be talking about my work on the limits of language generation. This is joint work with Kalavasis and Grigoris Velegkas. I'll begin with talking about some history of computer science and language generation. The crux is that computer scientists have been fascinated by language acquisition for decades. Shannon was an early pioneer in this area and was studying the predictability of English language. To illustrate that English is predictable, he used to play the following interesting game with his wife. One of them would take a sentence not known to the other and hide all but the first character of the sentence. The goal of this other person was to predict the next character, and then the second character would be revealed and the game would proceed, so on. This is, of course, very familiar to us today as the next token prediction game that is widely used to train language models. This game led Shannon to the idea of n-gram models. This is surprising because Shannon was developing these ideas in the 50s when computers were just coming about, and to realize the full potential of n-gram models, it would still take decades. The next milestone in the story is perhaps the work of Chomsky, who was the first to introduce a separation between syntax and semantics. In the same work, he also introduced a hierarchy of increasingly complex grammars, from starting from regular languages to context-free languages to context-sensitive ones, which had a huge impact on linguistics and arguably had a bigger impact on the theory of computation, where today we use these hierarchies to understand the computational power of different computing models. Our work will revolve along the next milestone in this story, which is a model of language identification by Mark Gold. I'll formally define the model in a few slides, but for now I want to highlight some interesting aspects of the model. This is one of the first precise models of language acquisition introduced in the literature, and it in some sense was ahead of its time. Along with Vapnik, Chermanenkis, and others, Gold was perhaps the first to introduce the idea of learning from samples, as opposed to explicitly defined rules. All of this work, of course, laid the groundwork for the celebrated PAC framework. But apart from this high-level direction, Gold's work also had a number of ideas which took a while to be fully developed in learning theory. Since the work of Gold, there have been a number of milestones, especially since 2010s, which lead us to today's modern language generators, large language models. These models can do very useful and creative tasks. Here, for instance, the model decided a creative task that it wanted to do, poetry, and accomplished it. The usefulness and potential of these models is perhaps best illustrated by the growing amount of investments in them. That said, to be deployed in complex real-world tasks, we still need to make these models much more reliable. Perhaps the biggest issue facing LLMs today is hallucinations. Broadly interpreted by hallucinations, I mean a language model outputting a string that is outside of the set of things we want it to output, or in other words, outside of the language that we want the model to be generating. In the early days, models used to make simple errors. Today, the models are much more sophisticated and much better, but they still sometimes lead to hallucinations in products, especially in contexts where it's not feasible to deploy state-of-the-art models. At the same time, avoiding hallucinations is an easy task. One can simply do it by limiting the range of outputs that the model can generate. This brings us to the main question studied in this work. At a high level, we ask, can hallucinations be avoided in LLMs while retaining their breadth? And is this possible by simply scaling the existing models and training sets? We will study this question in the model of language generation in the limit introduced by John Kleinberg and Selvin Volanathan, building on the work of Gold. Before getting to their model, I'll present Gould's model of language identification in the limit. This model is defined by a domain, which for now can be thought of as the um, set of all finite sequence strings of alphabets, and a concept class of languages, among which there'll be a target language that we want the language model to generate. For now, one can think of this collection as the set of all regular languages or all context-free languages. The learning game is a two-player game between an adversary and a learner. The adversary begins this game by fixing a target language, let's say K, whose index is I star. The game now proceeds in rounds. In each round, the adversary shows one example string from the target language to the learner, and the learner's goal is to guess the index of the target language. In this game, we say that the learner has won if it eventually guesses the correct index of the target language, and from that point on, never switches its guess. I have a few remarks about this model. First, it's important that the adversary presents a complete enumeration of the target language to the learner. It's easy to see that if the adversary is allowed to skip strings in the target language, then it's impossible for any learner to win. So for example, if the target language is the set of all natural numbers, then it's not okay for the adversary to present the following sequence of examples because it misses all odd numbers from the target language. On the other hand, this sequence is fine. As a subtle point, I want to mention that the following sequence, where odd numbers do not show up at any finite position, are also not fine and are not valid enumerations of the target language. To enable learning, we must allow the learner some form of access to the concept class, and we'll only use a very minimal form of access. We only require the learner to be able to answer queries of the following form. It can choose any string W and any language Li from the concept class, and it has an oracle which can answer whether W belongs to the language Li. Before proceeding to the model of language generation, I want to mention that the collections of languages that are learnable in the language identification model were characterized by Dana Angwin, and the characterization was mostly a negative result. It showed that almost all interesting collections of languages, even simple collections like regular languages, are not identifiable in the limit. Okay, with that, I'll move to the language generation model. This model has the same premise, a domain and a collection of languages, but now it's a game between an adversary and a generator. The game begins in the same manner. The adversary picks a target language and it proceeds in a similar manner over rounds. The only thing that changes is the goal of the generator. Now, instead of predicting the index of the target language, it only needs to output an unseen string from the target language. And we say that the generator has won if at some finite point, it starts generating unseen strings from the target language. This model of language generation makes a slight twist on the identification model. However, the surprising result of Kleinberg and Mullainathan was that this small shift leads to a dramatic difference in the characterization. In the generation model, all countable collections of languages become identifiable. Before proceeding to our model and results, I want to quickly overview a few properties of this model of generation. First, as we've presented it so far, it's a model of promptless generation, which is a bit far from the sort of language models we are more used to seeing. This, however, is a mild requirement because Kleinberg and Mullainathan showed that it's fairly easy to extend this model to a model of prompted generation, and all of our results will carry over to this extension. The second thing the model does is it's pretty abstract. It abstracts away all details of the training process, the architecture of the model, the fact that these models are typically next token predictors. These details are important, especially for positive results, where they impose important limitations on what the models can achieve. We will, however, focus on negative results. And here, this abstraction shows that the source of difficulty is at least not in these details that we are abstracting away. A third aspect of the model is that it's adversarial, which is perhaps not how data looks in the real world. Maybe a distributional model is more appropriate for real world data. Towards this end, in this talk and in the work, we consider a distribution model that we'll introduce soon. The final, perhaps more important caveat is that the model requires the language model to only output new strings, but does not require it to learn, in some sense, all of the target language. It does not require the model to have breadth. This is the sort of the main point of our work, and we'll look at different notions of having breadth and study generation with breadth. This brings us to the main question that we study in this work. We ask, is it possible to achieve language generation with breadth, or is there some inherent trade-off between having consistency, that is, avoiding hallucinations, and having breadth? With this, I'll hand over to Grigoris.
I will now take over from Anay and present our formal model. I will start with a statistical model of language generation and identification. Our statistical model is based on the foundational work of Anglin from the 80s and the recent work of Bousquet, Haneke, Moran, Van Handel and Yehudayo from 2021. Now the idea is that the adversary chooses a target language K, but instead of choosing an enumeration of that language, it is restricted to choosing a distribution over it. And what happens is that for every finite round T, the generator draws a fresh TIAD draw of samples from this distribution and outputs some subset of the domain, which we denote by script G sub T. Now the generator needs to satisfy some binary property P, and we do that in order to give a unified treatment of both identification and generation under various notions of breadth, as we will see later on. And the main thing what we wish to understand is that we wish to know as t goes to infinity whether the expected value of the predicate Pg of t goes to 0, and if it does, how quickly does this convergence happen. Now, in order to make things a bit more formal, we still denote the domain by script X and the countable collection of languages by script L. And the game between the adversary and the generator looks as follows. The adversary picks a target language K, which must belong to this collection, and a distribution over this language. By that we mean that for every element of the language, this distribution puts positive mass on it, and for every element outside of this language, the distribution puts 0 mass on it. And again, in every finite round, the generator draws a fresh batch of T samples from the distribution and outputs a subset of the domain script X. Now the generator wins in this modified game if it satisfies this property P as T goes to infinity, meaning that the expected value of P of G of T goes to 0. If this indeed happens, we say that the generator has rate R if the expected value of P of G sub T is bounded by R of T, appropriately reweighted by this distribution dependent constants capital C and little c. This rate of convergence will be an important object for the rest of the talk, so let me elaborate a bit more on that by considering the example of the exponential rate function. We say that the generator achieves some property P at an exponential rate if, for every target language K in the collection, and for every valid distribution over this target language K, there exist two constants, capital C and little c, such that the expected value of P of G of T is bounded by capital C times e to the minus little c times t. Now, the order of quantifiers in this expression is crucial. By that, we mean that for one distribution, we might have exponential decay with some particular constant. For example, in this blue curve, we have exponential decay with a constant 2. But for some other target language and some other distribution over it, we might have exponential decay with a different constant. For example, this red curve shows a decay with a constant 0.4. One important thing that we will use in this work is the notion of having no rate achievable, and by that we mean that this limit does not converge to zero. Having explained the statistical model in our work, I will go on and define formally the notions of breadth that we introduce. In our work, we introduce three notions of breadth. Perhaps the most natural one is what we call exact breadth, and by that we require that the generator contains all the elements of the target language K and nothing outside of it. Pictorially, the target language K is denoted by this green shaded circle, and the output of the generator is denoted by this purple dashed circle. Next, we introduce a relaxation of this notion, which we call approximate breadth, and that notion allows the generator to miss finitely many elements of K, but still cannot contain any elements outside of K. And notice that this is a strict relaxation because all generators that satisfy exact breadth also satisfy approximate breadth, but not vice versa. Finally, we introduce the notion of an ambiguous generation, and by that we require that the output of the generator is closer to K than any other language that is not K, and the closeness is measured with respect to the symmetric difference. Pictorially, we have the target language K, which is still denoted by this green shaded circle, some other language cell, which is denoted by this blue shaded circle, and still we can see that the output of the generator looks more like K than it looks like L. Having explained the notions of breadth we introduced in our work, I now move on to stating an assumption that we will use throughout our paper for all our lower bounds, which we call the MOP assumption. The MOP assumption starts from membership oracle property, and this is something that we assume all generators satisfy. By that, we require that for any string x in the domain, we can decide whether the string x belongs to the output of the generator. This is a mild assumption, since it is satisfied by a large class of generator, including but not limited to next token predictors. In particular, for next token predictors, we can look at the log probabilities in order to figure out whether something is in the output of the generator. But I want to emphasize that this assumption comes with laws of generality, since there are certain obscure generators for which this problem might be undecidable, and the decidability of this problem is related to the halting problem. Now Anay will take over and state our main results.
Next, I'll overview our results. Our main result is a characterization of a when generation with breadth is possible in the statistical setting. Consider any collection of languages. We show that if this collection is not identifiable in the limit, in the adversarial model, then no generator whose MOP is decidable can generate with breadth from this collection in the statistical model at any rate. On the other hand, if this collection is identifiable in the limit, then there is a generator whose MOP is decidable, which can generate with breadth from this collection, and in fact can do it at a nearly exponential rate. This stands in stark contrast to generation without requiring breadth, where we show that for any language collection, whether it's identifiable or not, there is a generator that can generate possibly without breadth from this language collection at an exponential rate. The characterization I presented is for the notion of exact breadth. We also give analogous characterizations for the other two notions of breadth we introduced. And these characterizations also hold modulo the MOP of the generator being decidable, and an additional requirement of the generator being stable. Due to the lack of time, I'll not go into the definition of stability, but I encourage you to look at the paper. The above characterization is not complete in the sense it does not apply to generators whose MOP is not decidable. This was extended by the work of Charikar and Paparaju and a follow-up work of our own to all generators, whether their MOP is decidable or not. Further, the above only looks at certain coarse notions of achieving breadth, either the generator having exact breadth for the whole language or having no breadth at all. It is possible to study more fine-grained notions of breadth, and this has been done by subsequent work in ICML by Peel, Raman, Reingold, and also by John Kleinberg and Fan Wei, where they look at the online setting and look at certain more fine-grained notions. Next, I'll present a short overview of the proof of our main result. This is mostly an outline, and Grigoris will later dive into a bit more depth. Our main result consists of two parts. The first claim applies to collections that are not identifiable and shows that generators satisfying a mild property cannot generate with breadth from these collections. A natural strategy to prove this is to take a generator, suppose that there is a generator that can achieve breadth, and somehow convert it into an identifier in the limit, which would then contradict the fact that the collection is not identifiable. To be able to get an identifier, we must be using some property of the generator G beyond that it outputs an enumeration of the target language. Because if we don't, then all we have access to is another enumeration of the target language, which in the online model we already had from the adversary. So I'll briefly discuss a couple of properties of the generators that we could use, and we have a more extensive discussion in the paper. The first property is perhaps that the generator is not adversarial. The enumeration it outputs is not specifically chosen for our learner. However, this does not seem too useful because there are simple collections that remain unidentifiable for many enumerations of the target language and do not require a very specific hard enumeration. The second property we could use is perhaps a generator is sampling its strings from some fixed distribution. The problem of language identification when the samples are the problem of language identification in the limit when the samples are drawn from a fixed distribution was studied by Dana Angwin, who showed that the characterization of identifiable classes remains unchanged in this model. So the fact that our generator is outputting samples from a fixed distribution does not help us create identifiers for non-identifiable collections. Hence, we must use some other property of our generator. And our first idea is to use this membership oracle access to the support of G, which, roughly speaking, provides us membership to the target language K. With membership access to target language K, it's not too hard to show that one can get an identifier for the collection in the limit. However, this is not quite enough to get our result in the statistical setting. Using the above sort of conversion, what one could hope for is to convert a generator that achieves breadth at rate K into an identifier that identifies at rate K. However, this is different from what we need to achieve a contradiction. To get a contradiction, we need an identifier that works in the limit. To see why this is not sufficient, let's consider the following possibility. It's possible that there is a language collection that is not identifiable in the limit, but nevertheless, in the statistical settings, becomes identifiable at some very, very slow rate r. This is not an entirely hypothetical example because it's true in binary classification, where there are many classes which are not learnable in the online model, but become learnable in this statistical universal rates model. So to prove our result, we take a different approach. First, I'll outline the approach for non-identifiable collections. Here, we first show that if a collection is not identifiable in the limit, then it's not identifiable in the statistical setting at any rate r. This is the key technical part of our result, and it strengthens the results of Angwin. Then we show that we show how to convert a generator which achieves breadth at rate r into an identifier which has rate r. This then is sufficient to conclude that because the collection L is not identifiable at any rate, we must not be able to generate it with breadth at any rate. Now I'll move to the second half of our results, where we look at identifiable collections and show that they can be generated with breadth at almost exponential rates. Here, the first step is to obtain an identifier at near exponential rate for the collection. This seems like the standard place where one can use an online to batch conversion, but in our model, there are several challenges. First, the generators in our model generators or identifiable in these models do not get any feedback, which can then be used to fix the size of the batches we need. Second, when we have a bunch of online identifiers that we have trained, we cannot simply aggregate them by taking the majority vote, because in our language collection, the target language K can be occurring at many indices, and each of the identifiers we have trained could be outputting a different index. Hence, we need some new way of taking majority votes. So we overcome these by using an online to batch conversion strategy with growing batch sizes to overcome the issue of having no feedback. And then we post-process the output of each identifier trained in a batch so that it identifies the unique smallest index of K in the language collection, so that all correct identifiers are outputting the same index. And then it's easy to take a majority vote. Now that we have an identifier that identifies the collection at a near exponential rate, it is easy to convert it to a generator with breadth, since generation with breadth is an easier task than identification. Now I'll move to some of our further results. Our first set of further results is rates for identification in this statistical model. Here again, we show that if a collection is identifiable in the limit, then it can be identified at near exponential rates in the statistical model. On the other hand, if it's not identifiable in the limit, then no generator can identify it at any rate. Note that unlike our main result, this result places no constraints on the generator. In particular, we do not need its MOP to be decidable. There are a number of variations of these results we prove in the paper. For instance, we show that the rates in the above result can be improved from near exponential to exactly exponential when we have certain special forms of access to the collection, or if the collection has a certain specific properties. I'll not go into these in more detail, but I encourage you to check out the paper. Our second set of results explores which collections can be generated with breadth when more information is provided to the generator. In particular, we look at a model where the generator is provided both positive and negative examples. Here, positive examples correspond to strings in the target language, and negative examples correspond to strings outside of the target language. With this twist in the model, we show that all language collections become generatable with breadth. In fact, they become generatable with breadth at an exponential rate. This sort of model is perhaps reminiscent of reinforcement learning with human feedback, which encodes some form of negative information about the language that the language model is supposed to be generating. And indeed, such proxies for negative examples have been found useful in practice, leading to reduced sample complexity of training language models empirically. An important empirical challenge here is to be able to extract such negative examples or other form of feedback at scale in real-world tasks. With that, I'll hand over to Grigoris to give an overview of the proof of our main results.
I will now take over and give some more detailed proof overviews of some of our main results in this work. I will start off by explaining our approach to get exponential rates for language identification. In order to do that, I will first start by explaining a general online-to-batch conversion that was proposed by Bousquet, Haneke, Moran, Van Handel and Yehudayov in the context of binary classification, and has since then been applied to several works in the line of work on universal rates. In this framework, one first estimates some number T star, so that when the learner draws TIAD samples from the target distribution, then it wins the online game with some good probability that is bounded away from 1/2. Then one splits the input into T over T star non-overlapping batches. Subsequently, one runs the online game on each batch independently. And the final step is to aggregate the outputs of all these games by taking, for example, the majority vote of all the predictions. Unfortunately, there are two obstacles to applying this framework in our work. The first obstacle has to do with the fact that we cannot estimate this time T star because we do not have any feedback on the predictions that we make. In particular, in the work of Bousquet et al., they could obtain feedback by using the fact that they have both positive and negative examples, but in our work we only have access to positive examples, so there's no way to simulate that type of feedback. The second obstacle has to do with the fact that we have multiple copies of the same target language, so even if the outputs of the game are correct, they might correspond to different such correct indices, so one cannot immediately aggregate all these outputs together. In order to circumvent these obstacles, we propose the following modified online-to-batch conversion. Firstly, we choose the time T star as an increasing function of T, meaning that T star is no longer a constant as in the previous framework of Bousquet et al. Then we still split the input into T over T star many non-overlapping batches, and the reason why we get almost exponential rates instead of exactly exponential rates is that T star is no longer a constant. Then we run the identification game on each batch independently, and before we take the majority votes over the indices, we apply a post-processing procedure on the outputs of all these games in order to ensure that correct cases are mapped to the same index. What I described proves the first part of our result for the statistical rates of identification, which states that if the collection L is identifiable in the limit, then there exists an algorithm which identifies L at any exponential rate. The second part, which says that if L is not identifiable in the limit, then no algorithm can identify L at any rate, is the most complicated element of our work and follows a conceptually different approach from Bousquet et al. Since there are time constraints for this video, please feel free to ask Anay or myself either at the conference or at the poster session for more details. Next, I want to point out that we can get exact exponential rates for identification, but we cannot do that in a black box way. We do that with a particular algorithm. Now, having explained the exponential rates result for identification, I want to move on to explaining the exponential rates result for generation. Now, the previous modified framework that I showed you does not work here. And the main obstacle is that we cannot aggregate generators in a black box way. And this was made more precise in a follow-up work with Steve Haneke, Amin Karbasi, and Anay. And in order to circumvent the issue of aggregation, we propose a perhaps much simpler solution, which avoids the aggregation altogether and shows that the online algorithm from Kleinberg and Mulanathan gives exactly exponential rates in the statistical setting. This is perhaps interesting because, to the best of our knowledge, is the first result in the universal rates framework, which shows that one does not need to go through an online to batch conversion and can simply run the online algorithm in the batch setting. In order to explain to you how this result works, I will first point out how the KM24 algorithm works. Now, given a set of elements of the target language K, let's call that S sub T, the KM algorithm creates the set of critical languages and then outputs an unseen element from the highest indexed critical language. The set of critical languages is defined in the following way. Firstly, it is a subset of the first T languages of the collection script L, and every language Li in this set of critical languages satisfies these two main properties. Firstly, this language Li is consistent with the current input S sub T, and secondly, for all languages J that come before Li in the collection script L, if Lj is indeed part of the set of critical languages, then Li has to be a subset of Lj. So critical languages create a set of inclusion among valid languages. Now, the key property that the KM24 algorithm has is that for every target language K, there exists some finite set, let's call it S superscript K, such that if the set of elements S superscript K appears in the input stream, then the algorithm always generates correctly. What we show in our work is that every algorithm which satisfies this property achieves exponential rates by just running it as is in the statistical setting. I will now wrap up the presentation by mentioning some directions for future work. Firstly, it would be interesting to obtain complete characterization for the following problems. The first question has to do with characterizing stable generation. By that we mean generators who stop changing their outputs after a finite number of iterations in the online game. In a follow-up work with Anay, Mehrotra and Kalavasis, we have made some progress on this problem, but the complete characterization is still open. Next, the other problem that we do not have complete characterizations for has to do with obtaining fine-grained trade-offs between hallucinations and breadth. Some partial results in this direction are in this follow-up work of ours, as well as in the work of Charkar and Paparazou and Kleinberg and Wei. In order to circumvent some of the lower bounds that appear in our work and other works, one can consider generators that are allowed to output multiple responses, and only one of these responses needs to be correct. We don't know how the landscape looks like under such a definition, so it would be very interesting to explore this direction. And next, it would also be very interesting to develop computational efficient algorithms in some more structured settings. Finally, it would be very interesting to know what type of feedback is useful in generation, and some partial results in this direction have been given by the work of Charkar and Paparazou. Thank you very much for attending our presentation. If you're interested in the direction of language generation, we would like to announce that Moses Sarikar, Anay Mehrotra, Chirag Babaraju, Charlotte Bill and I are organizing a tutorial at Cold this summer, so we would be very happy to see you there. We also have a website online that contains material related to language generation, so please visit the website. Thanks.